Hello, everybody. Oh, that's loud, but it's good, yeah. So my name is Alexander or Sasha, and I'm from University of Southampton, and also a member of CERN and, Rutherford Lab. So originally I'm, from particle physics, so I'm theorist. But only last 10 years, because I've been in Southampton for 20 years, I touched cosmology. I started enjoying cosmology, and then I realized that particle physics and cosmology, they are very tightly related, and there is a much more excitement coming when you actually know both, when you study both. So, and this excitement I would like to pass to you, because interestingly, you can learn about the electromagnetic field, which is here, there's this topic here. In particle physics, electromagnetic field is actually quantum field. It's actually even at a higher level. But you can learn about mysteries of the universe. And that's what I wanted to talk about today. So to start with, this is my story in one slide, actually, so in case of you're impatient. So on one hand, we have the oldest light coming from the Big Bang, and I will be talking about this called CMB, Cosmic Microwave Background. And actually, just could you raise your hand who heard about Cosmic Microwave Background? Okay, quite a few people, yes, so actually almost everybody. And how to connect this light to ordinary light and to much higher energy light or energies at Large Hadron Collider, and what is common. And so I'd like to understand what mysteries the ancient light coming from CMB can reveal. To start with, I just like to talk about normal phone, and does your phone produce any electromagnetic field or light? The answer is yes, but actually the range of the energies or range of the wavelengths is very different. It could be visible light, like you look at your screen, and here it is. It could be Wi-Fi, Bluetooth. It could be heat, infrared radiation. All of them, they have in common photons or electromagnetic field, and which have different energies. For example, visible light has only 2 electron volt energy, and actually, yeah, the units are very important when I say electron volt. So electron volt is the energy which particle physicists use. It's when you have potential with 1 volt, an electron passing this potential and gets this energy. And this energy will be 1 electron volt. And this is the energy, typically, you see the visible light, and the photon coming to you has the energy of the order of 1 electron volt. So 1 electron volt is visible light. So just to compare with other light. So this means that if you have some infrared or Bluetooth, it's much less energetic photons than visible light, so visible 2 electron volt. And heat, it's more energetic than radio waves, but still less energetic than visible light. Now, the range of the energy of the light, which is a common currency. So the common currency is the energy. And the energy can be ranges from very low, but there are small fonts, but I will tell. So we can measure it in the 10 to the minus 6 electron volt, this is radio waves, or Hertz, 10 to the 9 Hertz. Go to the visible light, 2 electron volt, 10 to the 14 Hertz. And we can go to X-rays, and we can go to gamma rays. So gamma rays, for example, 10 to the 19 Hertz, or mega electron volt, up to mega electron volt. And then we're going to the highest energy available at Earth, which is 13 tera electron volt, or 10 to the 27 Hertz, or 10 to the 13 electron volt. So tera is 10 to the 12. If we have 13, so it's 10 to the 13 electron volts. Crazy energies. And of course, the most energetic photons coming from Large Hadron Collider. So what's in common and why? So first, just quick poll. Please raise your hand if you think that photon is the wave, particle, or both? Yes, yeah. So everybody, that's why we're here. That's the right answer, so you understand it. It's wave, particle, and both together. And this is the really important to understand, because on one hand, photon is the wave packet. It's localized in space. But on the other hand, the collective movement of the photons will be represented by the electromagnetic wave. And in the next slide, I just want to, well, kind of show this. So, okay, so one photon localized in space. Many photons can make electromagnetic field. Like yesterday at stage D, we've been doing I mean, anybody was there? I don't know. There was, yes. We've been. So many people there represents photons, and when you do collective movement with about same energy, this would be electromagnetic wave. So photon can do this. I mean, so photon has a duality. Now, what about time? One important message is that light is a time machine. So in one direction, there is no mysteries. You cannot look kind of meet yourself. There is no possibility. There's causality problem. But you can look at the ancient light coming to us from the time which I will be talking about when the universe becomes transparent. And moon, few seconds, sun, 8 minutes. This is the time which photon travels. So the speed of light is actually constant. It is the same. But the time it takes, say, 2 million years to get to Andromeda, and 13.8 million years to the point, well, to the point when the universe becomes transparent. It was a long time ago. It's almost 14 billion years ago. So picking up this time, picking up those photons, we actually can reveal the picture. We can see the past. And one of the things, I just want to say that what is the oldest light? I just mentioned CMB. So it's called cosmic microwave background. And I will be devoted few slides about this. So what happened with the universe become transparent and why it became transparent, okay, after the Big Bang. So first of all, this map. This is not an ordinary photograph. This is a series of the sky map survey of the most ancient light which we have, which travels to us almost 14 billion years now. Let's talk about this. Let's talk about, and it's called cosmic microwave background. Well, let's talk about the energy. But first, before we talk about CMB, I just want to discuss how universe become transparent. So we know that universe was very hot, and there was a plasma. When there is a plasma, which means that atoms of hydrogen, for example, they've been ionized. There was ions, charged particles, and light could not propagate freely in plasma because there's a lot of charged particles in this soup of. So then universe slowly cools down and atoms recombine. So proton will be catching electron and recombine to hydrogen atom. Once this happens, shortly after that, well, photons can freely propagate in the space. And starting from this point, just from the surface, we can observe light. And this is CMB. The time when atoms of hydrogen was recombined is the time of CMB. And this happened about, 380,000 years after Big Bang. At the same time, this happened about almost 14 billion years ago. And one thing which I will introduce, this is a redshift. There's probably only one formula. The redshift called Z. It tells that how much universe expanded by which linear factor. So if, for example, if redshift is equal to 1, universe is expanded by a factor of, at the redshift 1, universe was 2 times smaller. And the CMB time corresponds to redshift 1100. This means that when the first light was released after the atoms of hydrogen was recombined, the universe was 1100 times smaller than now. This means that there is a very important effect related to that, because the speed of light stays the same, but while universe expanding, the wavelength of the light becomes bigger, which means the frequency of the light becomes smaller. And this is the whole point. So early time, light has a high energy. The energy of the cosmic microwave background was 1,100 times bigger in the past, and now it becomes 1,100 times smaller. Now, how do we know the say, age of the light coming to us? This is a very tricky question, because individually photon does not carry life stamp, or time stamp. Sorry. So, but we know if we collectively pick up photons from spectral lines, we can shape of the radiation of the spectral line from the hydrogen. And for example, now it will look like this. But if it was released long time ago, when the universe was smaller and then it expanded, the universe stretches, and with stretching of the universe, the length, the wavelength also stretches. So if it's stretched by some factor, say 4, it will become like this. And that's how we know actually the age of the photons. Besides this, we also know that if we look at the cosmic microwave background and distribution of the photon and wavelength, it's almost perfectly black body radiation. With the temperature now, 2.725. That's it. Well, we can measure, actually it's measured up to 6 digits. Well, but also these ripples represent the crucial information. It represents the temperature fluctuation along the sky. So the blue low temperature, the reddish high temperature. And this is the key point of the whole cosmology. This is the actually key point of the whole talk today. So first of all, we know the temperature of the universe now. We can go back and say that, okay, if the temperature of the universe was, E is now 2.7, that at the CMB time, it was 1,000 times bigger, or a little bit more, so about 3,000 Kelvin at CMB time. This is the temperature at which atoms of hydrogen recombined. And this is the thing. Of course, what I wanted to say now, knowledge of these ripples and origin of these ripples, this is temperature fluctuation at the level of 10 to the minus 5 kelvins. So it's extremely small fluctuation, but they're crucial to understand actually why we're here, not even just normal cosmology. And this is the procedure. Maybe I will skip this slide. So the idea is that we know cosmic microwave background and temperature fluctuation. We undo expansion, and we learn that, well, at 3,000 Kelvin, we get photons start freely propagating. So this is the time and temperature at which we can actually see the first light coming. So the light initially had, sorry, I clicked a little bit earlier, but yes, that's why. The light initially at CMB time has 3,000 Kelvin. Now, these ripples in the temperature fluctuations at the level of 10 to the minus 5. So average temperature 2.7 Kelvin, but it has fluctuations. And these ripples of temperature fluctuation, they propagated along the, well, this is the whole history. This is in these 3 meters, this is 14 billion years of the history. So we're somewhere here. So, and these ripples propagate and create the structure of the whole, well, stars and galaxies has been originated from this. Now, I wanted to, okay, one second. Something supposed to start. Something interesting. Oops, this is not good. It was working. Shall I? I'm sorry. Oh, yes. Okay, maybe I skip this. This is not good. Because maybe computer is old. Please. No, it's just I'm taken to computer. It's maybe okay. I'm going to try again. 1 second. It should not take long. Okay, I will restart it. And it will be, sorry for that, but this is kind of happening. Okay, very good. Let's hope that it will work now. Come on. I think particle physicists should buy the better computer because I enjoy my old one, and that's why it's yeah. Okay. What? That's okay. Yeah. Let me do this. I will. I have a nice video about. Okay, but we don't have much time on this to play around with this. Yeah. I will. What I will do, I will quickly restart. It will take 1 minute to restart, but it will be, yes, it will be more reliable now. Yeah. So meanwhile, while it's restarting, I just want to say that we stopped at the very crucial point. Maybe, well, it wants us to think about this. That ripples in the cosmic microwave background gave a seed for formation of the galaxies. And without the seeds, there will be no galaxies, no us. But the seeds and ripples in cosmic microwave background, ripple means ripple in temperature, they couldn't produce the galaxies and structure by themselves. They needed help, because it turns out that if it would be ordinary matter which related to these ripples, then there will be not enough time to form galaxies. What happened? We need help with something, and this something, and we know we can do theoretical calculation, and we know that this something is very important. It's called dark matter, and that's. I'm coming to this. Okay, it should work now. Yeah. Okay. This is background, nice background, good. Let's try. Okay. Ivan will not be using this one. Okay. Let's do this now. Yeah. It's much quicker. So, we stay here and then we talk about the formation of galaxies from these ripples. So this movie tells us how the WMAP experiment, this is the satellite which has been taking the picture of cosmic microwave background, reconstructed the past, how it actually served as a time machine. This is quite amazing because this is, these flakes. Well, first universe was dark because CMB, cosmic microwave background, are just photons and nothing else, so it was still kind of dark. But then at some point the galaxies and stars started being formed. So this picture tells that the cosmic microwave background formed here. This is the point when the universe became transparent. And then stars start and galaxies start forming, and we reach today. So we can actually make a movie, and this movie was reconstructed by looking at the age of the spectra and photons coming. That's why we can see how stars has been forming, galaxy has been forming. And this has been done using this satellite. So this was an actual experiment which has been surveying the sky and reconstructing this time. And so we have this picture. The message here that in order to convert ripples in the cosmic microwave background fluctuation into structures like our galaxy, you need the help from something which we call dark matter. Without this, there will be no structure, there will be no us. And just to kind of highlight, so ordinary matter, what is the ordinary matter? This is the protons and electrons which form a hydrogen atom, and they interact with the light. And dark matter, which something which helps to form all the structures, this is something which do not interact with the light. So it's not dark, there's no color. It simply does not interact with the light. It does not carry the charge. And this dark matter was kind of coupled to the temperature fluctuation of CMB, was kind of following these ripples and forming the seeds for galaxy formations. So there will be, so dark matter was follow the web and ordinary matter falls in and then galaxies switch on. No dark matter, there will be no us. So let's just look. So no dark matter, ordinary matter only. That's what universe would be. There will be no time to form galaxies and stars, etc. Dark matter created the gravitational wells, follow the ripples of the cosmic microwave background, and it created the structures. So this is one of the main messages here. So no dark matter, no early gravitational wells, no galaxies, no stars, no us. So we learned this from the cosmic microwave background ripples, and we learned it from structures, well, large-scale structures. Why do we know there is dark matter? Not only from cosmic microwave background, not only even from large-scale structure formations. We know this from the rotation of the stars around the galaxy, because there's a missing mass which dark matter contributes to, which makes stars rotate quite fast, faster than we expected from ordinary matter. There's the same thing happening, well, at the larger scale, and also we observe gravitational lensing coming from something, were arranged by something which called dark matter. And just the budget, the atoms and baryonic matter, whatever, if we sum up stars, planet, black holes, which we also know what it is, believe me, it will be only about 5% of the whole matter of the universe. And the dark matter contributes about 6 times more, well, 5-6 times more. And there is something which we call dark energy, which I will mention in 1 minute after, well, when I go to the end. This is another mystery. So, how we can search for dark matter, which is responsible why we're here, which was following these ripples of the cosmic microwave background. We need energy to create dark matter on Earth. Well, and Einstein taught us that energy is connected to the mass. So we can convert energy to the mass and create dark matter at Large Hadron Collider. That's the key point. So you convert energy into a bunch of particles. These all kind of traces are particles. So you have crazy large energy, which is 13 tera electron volts, or almost 14 tera electron volts, and this energy is converted to the particle masses, including, hopefully, dark matter. And this is Large Hadron Collider kind of pre-accelerator. This is another further accelerator, but it's not the main ring. And then you have another SPS. This is the main pre-accelerator. And then you have a proton, which consists of 3 quarks. Well, and this is just small reconstruction of one event of the Higgs boson production. So you can convert the energy into particle mass. And this is longest lines are actually 4 muons coming from 1/2500 GeV object, which is called Higgs boson, which was discovered in 2012. In analogy, we can create another massive particle, hopefully dark matter, and discover it. So that's the hill point. And I have still 4 minutes. All right. Yeah, that's okay. That's yeah. So at the LHC, we can convert energy into mass. But how we discover dark matter? First of all, dark matter is invisible to detector. How we can see invisible? Funny thing. Well, we can see invisible by missing transverse momentum, because the idea is that 2 protons collide. 2 protons collide, and in transverse plane, the sum of the momentum is 0, because they are going along one line. So then you produce a bunch of particles, and you count the energy and momentum in transverse plane. And then you find that, okay, so missing transverse momentum, this is the, well, I should put maybe a dashed line here, which could come from dark matter, compensate, but we don't see this. We see only unbalanced tracks from charged particles. If it's unbalanced, something invisible, something neutral was produced, and this is the example how we can see, in quotes, dark matter. We can detect it. We don't see, but we can detect it. That's a funny thing, but yeah, that's how we see. So after collision, we can count the missing transverse momentum and find dark matter. So the mystery is still open. We don't know what dark matter is. We know it interacts gravitationally from the cosmological experiment. We know that CMB, cosmic microwave background, which, well, there is a lot of studies and spectra on this. Actually, they require dark matter, well, and it's encoded in CMB, and then it propagates to large-scale structures, creating galaxies, stars and galaxies, explaining why we're here. So now you can look at, still continue looking at dark matter cosmologically from galaxy surveys. But there is two main kind of searches, or maybe three main searches on Earth for dark matter. One is, of course, Large Hadron Collider and missing ET, missing transverse energy, or missing transverse momentum, which is similar. You can look at dark matter in the underground experiments, because dark matter, like neutrinos, they can go through the Earth, but if you have a huge detector underground to shield from other backgrounds, you can look at the dark matter scattering on the nuclei. And then you can look at the ionization and rare events, and this way you can also detect dark matter. It's called direct detection dark matter in the underground experiments. There's also indirect dark matter detection, which called dark matter can still kind of annihilate and produce energetic particles, and there's another experiments on Earth, like in Antarctica, experiment called Ice Cube, looking at high energy particles coming from possible dark matter annihilation in the skies. And so the ancient light reveal that dark matter mystery. So CMB and the oldest light from Big Bang revealed this mystery. So we need to find it. And I'm sure that all these searches will lead to some discoveries, and hopefully soon. That's a very important thing. As I promised, I just want to say 1 minute about dark energy. It's another mystery. It's not related to dark matter and CMB. But there is something which is called cosmological constant or dark energy. So it's Einstein introduced it, then thrown away, then brought it back. So think about the constant energy density in the universe, just constant energy density. Universe grows, but energy density remains constant. It's a bit non-conservation. Naively, it's non-conserved energy, but it's not quite right. It's actually everything is conserved. It creates kind of negative pressure. It creates kind of mystery addition, like 70% addition to the all total budget of the universe. And this is another mystery which nobody knows how to solve. Dark matter searches and revealing this mystery pretty much straightforward, and I think soon we will uncover it. Dark energy is the next step to understand. And I just want to thank you for your attention. Thank you very much. This is my email, and this is my profile at the university, so you can just look and ask further questions and Q&A or email, whatever.